I will talk about our work on characterizing superconducting materials and essentially quenching field. And I have to point out that this work is really the production of Chi-Chiang Go, is one of our postdocs. I will talk about our motivation, system description, overview of the cavity design, and then we will talk about a little bit about our experimental results. In the context of this experimental result is mainly to characterize the system rather than the system to characterize these experimental results at the moment. And then Choshi Tajima, I'm sure, will summarize some of the really new results from that system in his talk. So the goal of this test is really to characterize the quenching limits of superconducting materials. And the idea is that you don't have to wait until you build the whole cavity before you understand which materials and how to characterize, especially materials like stratified layers of different materials with dielectrics and so on and so forth, novel materials, which will take years before you can build a full cavity made out of these materials. Two things we wanted to have is a quick testing cycle, and the other thing is to make sure that we don't have a limitation on temperature. We can go up and down in temperature beyond the 9 Kelvin of niobium. So the system is basically composed of real copper, and the basic idea is that you can make, at least this was the original idea of the whole system, is that we characterize the samples with a very short pulse from a very high power system, and in that case all thermal effects and everything in the system is not a factor in determining the quenching field. Well, it turns out that this is cannot be done. It's far away from reality. But without further ado, this is the basic cavity structure. And this cavity structure basically is a TM01 like mode with 3 lobes in the radial direction. It's actually very much a spherical cavity. It's almost exactly spherical except with this opening and this small protrusion, so we can put the flat sample. And the reason for this spherical structure is that it makes the field on the sample much, much higher than the field on the surface of the cavity. And it also makes the part that's responsible for the quality factor of the cavity much more dependent on the sample than the rest of the cavity, which is made essentially out of copper. That's quite different than most other cavities. And then in this case, we are not limited at all to any value. The value of the Q when this part is completely superconducting is about 350,000. And for cavity working at 11 gigahertz, that's a very, very large number. This is the cavity structure. Essentially, it's put on a pulse tube that cools it down from room temperature to about 3.5 Kelvin in about an hour or so. And we change the sample from room temperature to vacuum. The whole process takes about 3 hours at most to go to about 3 Kelvin from the sample being in your hands. The system has its own roughing pump. Everything is self-contained in one single structure. And what you see here is the body of the cavity. And this body of the cavity gets inserted into the pulse tube, and the head of the pulse tube is here, and the sample lies around here. This is the cavity itself, and this is the cover of the cavity that contains the sample. And the sample is directly contained, touching the head of the pulse tube. The structure of the system is we have this klystron that can produce up to 50 megawatts of power. It goes into a directional coupler to estimate the power, and then it goes into this other directional coupler. It's about 10 dB. We throw away 1/10, we throw away 90% of the power we're using from this klystron, simply to, as much as possible, isolate the cavity from the klystron. As it turns out, the reflection, because this huge quality factor of the cavity gets a huge response, a spike at the beginning of the cavity when it's charging, affects back the klystrons, and we need to isolate that as much as we possibly can. So this cavity, this directional coupler, does this isolation for us. Furthermore, in situ, we can turn off the klystron, attach a network analyzer here, and then characterize the cavity at low power and understand the Q. And it turns out that we can do almost reasonable job in measuring the residual surface resistance. This is an added bonus. We didn't realize that we can do that because we thought that this would be completely dominated by copper. But it turns out that we can really, with a small variation, understand the residual surface resistance, especially when it became very high when we did this experiment. Furthermore, it turns out that in order to do this experiment, we started with a very simple approach. We just tune it with a network analyzer, tune the frequency by hand and so on and so forth. And it turns out that that's impossible. Several things needed to be happening. There is have to have a true control system for this structure. And that control system really does two things. First of all, it tracks the klystron to make sure that the frequency is exactly tuned at the resonant frequency of the cavity. Furthermore, it makes a compensation for the reflection that goes back to the klystron and comes back to the cavity, and understand to adjust the phase correctly on the cavity all the time without having to change the structure of the cavity itself, or to change the external quality factor of the cavity itself. Hence, there is an arbitrary function generator with amplitude and phase that senses what comes back to the klystron, modify what goes inside the klystron, and correct this in a feed-forward loop.